You might want to watch carefully on the board. So what are we trying to prove here? Let me move this over here. X1 to X and normal, mean theta, just keep it simple, I'll make the variance 1. And we're going to use L2 loss. The loss function. This. And our theorem is that taking theta hat equals to x bar minimax. This example, we can't deal with it the same way we did before. So finding a Bayes estimate of constant doesn't work, it turns out. So I'm going to show you kind of a more general strategy here for showing something as minimax, which is take the problem of finding the minimax risk and divide it into 2 tasks, which is find an upper and a lower bound. So remember the definition. This is the minimax risk. The smallest is the maximum risk. So what I'm going to do is find an upper and lower bound separately. So how do I do that? How do I find a convenient upper bound, lower bound? What I'm going to do is find an upper and lower bound that are very close together. So kind of sandwich Rn between 2 numbers. Well, so first of all, let's look at this Rn. We get an upper bound. Look at this. This is the inf over all estimators of the maximum risk. If I just pick an arbitrary estimator, its maximum risk has to be bigger than this, right? This is the smallest possible. So an easy upper bound is just to take the maximum risk of some arbitrary estimator. So let's call that estimator beta max swap. So this is an arbitrary, any conveniently chosen estimators. It's not really going to be arbitrary, you have to choose it carefully, but I mean this inequality is true for any estimator. This is true for any estimator. So you pick any estimator in the world you want, you compute its risk function, you take the maximum. That's got to be bigger than or equal to the minimax risk. Because the minimax risk, by definition, is the minimum of this over all estimators. So any one estimator has to be bigger than or equal. So that's one way to get an upper bound. Obviously, to get a useful upper bound, you have to pick that in a clever way, but that's certainly an upper bound. Here's another way to get a bound. This would be a lower bound, which is pick any prior, I. Any prior, I, and get the corresponding Bayes estimator. And now, compute its Bayes risk. So compute, remember that was denoted d theta. And I claim that's a lower bound. And why is that? Let me show you why that's true. Let's just look at this definition again. So this is there's the definition of minimax risk again. This is a maximum. The maximum is always bigger than or equal to its average. So if I replace this with the integral, then I'm computing the Bayes risk of this estimator here. So this is bigger than or equal to. Can you write that down? This is saying that the maximum is bigger than the average. Okay. But this is the definition of the Bayes risk of this particular estimator theta. well, now we're looking at the Bayes risk of an estimator theta hat, then we're taking the minimum over all theta hats. What's that? That's the definition of the Bayes estimator. The Bayes estimator was the theta hat that minimizes this. So this is the smallest you can make the Bayes risk is the Bayes estimator. And this is minimized by theta hat. So, sort of just by definition, we have kind of two bounds. Take an arbitrary Bayes estimator, compute its integrated risk, its Bayes risk, that's a lower bound. And pick an arbitrary estimator, compute its maximum risk, that's an upper bound. Now obviously, if I pick poor choices, these could be very far apart, in which case I have no information about this. But if I pick clever choices, these will be close together. So let's try it in the normal. So for the upper bound, I'm going to pick what's probably an obvious choice. Let's pick as our arbitrary estimator x bar. And what's the risk of x bar? Well, risk for L2 to L2 loss is mean squared error. Mean squared error is the bias squared plus the variance. And what's the bias of this? 0. So the mean squared error is the variance, which is 1 over n. So now we have an upper bound. So let's. Now if I picked a different estimator, I'd have a different upper bound. Lots of upper bounds. This turns out to be a good choice. I kind of know the answer. All right. Now, to get this lower bound, I have to pick an arbitrary prior. Well, we're probably going to pick one where we know how to do the calculations. So I'm going to take the prior to be a normal with mean 0 and some variance c squared. Okay, so there's an exercise we talked about. I hope everybody's done it now, because it might be on the test, which is if I give you a normal prior and a normal likelihood, I pointed out that just doing some algebra, you can compute the posterior distribution, and it's normal. Okay, so under this prior, posterior is normal with some mean and variance. Let me just call it A and B squared. And we want the Bayes estimator. Well, what is the Bayes estimator for L2 loss? The Bayes estimator is the posterior mean. So the Bayes estimator is this mean. And if you look at if you actually look at what this is, hopefully you've done the calculation, it's a simple combination of the prior mean and the MLE, which in this case can be written because the prior mean is 0. Let's write it this way. So this is, again, if you've forgotten this calculation or didn't do it yet, just take the likelihood, multiply it by the prior, and then rearrange it until it looks like a normal. There's a little bit of algebra. You see it's a normal. Thinking of theta as the random variable, it looked like a normal. With this as the mean and some variance. I can write down the variance here. It's not important for what we're doing. And we know that the posterior mean, the mean of the posterior is the Bayes estimate, so this is the Bayes estimate without prior. Now, according to this inequality, what I have to do though is get the Bayes risk of this estimator. What does it mean to get the Bayes risk? Well, I'm going to first find the risk, and then I'll compute the Bayes risk. This is a good exercise, actually, this thing. So, I'll go over here, I'll just continue on here. So how do I get the risk? You know, if you were asked, oh, I don't want to test, get the risk of this estimator. The risk, what is the risk again? It's the mean squared error, because we're doing L2 loss. And so, we know mean squared error is pretty easy because I just take the bias and the variance, right? And so the bias versus the variance. So let's work out the bias. minus theta. But when I take the expected value of this, the only thing that's random here from the point of view of the model is x bar, and its mean is what? Theta. So it's n c squared theta over 1 plus n c squared minus theta. And then if I pull this together, what do I get? I get minus theta. So that's the bias of our estimator. It's minus theta over 1 plus n c squared. Notice that, just for future reference, the bias in terms of the sample size is something like of order 1 over n. Just keep that in the back of your mind. Future reference. That's a side note. All right, now I need to compute the variance of this. Well, the variance of this, this is a constant. So the variance of this whole thing is this constant squared times the variance of x bar. So the variance is that constant, so it's going to be n squared c to the fourth 1 plus n c squared times the variance of x bar, which is just 1 over n. Okay, now the risk in this case is the bias squared plus the variance. If it wasn't L2 loss, you'd have to actually just take the loss function and take its expected value directly. You can use the bias variance there. So if I square this and add it to this, I'll just tell you in the end what it turns out to be. After a bit of algebra, you get theta squared plus n c to the fourth. Nothing too intuitive, it's just kind of grinding through. So again, I just picked an arbitrary prior, found the posterior, got the mean of the posterior, that's my Bayes estimator. Now I forget where it came from. Somebody just handed me an estimator, and I computed its risk. But that's not quite enough, because that inequality says I need the Bayes risk, which means I need to integrate this with respect to the prior. So I need to say, what is, so the Bayes risk of the Bayes estimator is the integral But just think about this. This is just a normal distribution. Remember, we took the prior to be theta as normal with mean 0 and variance c squared. So we're really just taking the expected value of this quantity and treating theta as a random variable. That's normal. So I just need to really just think about, well, this is the only thing that's random here. So I really just want, what's the mean of theta squared? So this is, in other words, I can rewrite this as mean under the prior, let's call that e sub pi, theta squared plus nc 4, oh wait, that's nc to the fourth. Yes, there's a fourth here. Now think about the prior for a second. The prior, remember, is this. So with respect to the prior, what is the expected value of theta squared? C squared, right? It has mean 0. So the second moment is just the variance is c squared. So this is c squared plus nc to the fourth. But now look, if I pull out a c squared here, then I have c squared times 1 plus nc squared, and I have 2 of those down here, so that just becomes this. So all of that calculation was just to get this final expression, which is the left-hand side of this inequality. So what we've got, therefore, is an interesting inequality, which is whatever the minimax risk, I don't know what it is yet, but I know it's less than or equal to 1 over n, and it's bigger than or equal to this, but C was arbitrary, right? I picked an arbitrary value C for the standard deviation. So this is true for every value of C. So in particular, if I take the limit as C goes to infinity, well, of course, that doesn't change, that doesn't change. But what happens to this is then it goes to infinity. Sorry, C goes to infinity. 1 over n, right? Therefore, I've concluded that the risk is less than or equal to 1 over n and bigger than or equal to 1 over n. The only way that can happen is that the minimax risk is equal to 1. The reason why finding a Bayes estimator directly and just getting a consequence doesn't work is because we're on the whole real line, and intuitively what you would need is a prior that's kind of uniform over the whole real line. There's no such prior. So when that happens, we use this upper and lower bound kind of argument. In fact, intuitively, when I take a limit as C goes to infinity, it's kind of like I'm writing a normal target, flatter and flatter. But it's better to think of it, I think, in terms of just, I've sandwiched it between an upper and a lower bound, and from that, I'm able to deduce the exact minimax risk. So now we know the minimax risk is exactly 1 over n. Now, to find a minimax estimator, all I have to do is find an estimator whose maximum risk is 1 over n. Is there any estimator whose maximum risk is 1 over n? X bar, right? So if I take theta hat be x bar, then its risk, it doesn't even depend on theta, but I'll put the soup there anyway, is 1 over n. That's equal to the minimax risk. So now we've done two things. We've found the minimax risk in this problem, which is 1 over n, and we found an estimator whose maximum risk is equal to that. Therefore, x bar is the minimax estimator. So it is essentially unique. So the proof in the notes is similar to this, but I think the way I did it here, by making it explicitly this upper and lower bound argument, I think is a bit clearer. Okay, any questions about that? All right, so you can see here that finding the minimax risk or finding the minimax estimator is kind of an art, right? I mean, if I pick a different estimator for the upper bound and a different Bayes estimator lower, I might not have got something that's close together. And so sometimes it can be hard to do this. That's why people write research papers about it. You'll see lots of theoretical statistics papers about finding the minimax risk of this problem, because sometimes it's so hard that you have to actually write a research paper about it. So don't be dismayed if it seems a little bit not automatic. It just isn't. It's just, you know, it can take some playing around to solve any problem. You might wonder though, isn't there something which is at least approximately minimax in general? And if we stick in our, remember we're still talking about parametric models, then it turns out under some conditions, the MLE, I'm going to say, is approximately minimax. What does that mean? Now, it turns out that making this precise is pretty complicated. There was a mathematical statistician named Lucian McComb, who was at Berkeley, who made all of this very precise a number of years ago. Not just him, but other people. That make say, what does it mean to say that the MLE is approximately minimax? It just turns out it's quite complicated, actually. So it's certainly beyond the scope of this class. If you take our advanced statistical theory class, depending on who's teaching it, they often go into the details here. So making that statement precise is very difficult, but it's true. There's a sense in which the MLE in well-behaved parametric models finite dimensional parametric models is approximately minimax. But there's some assumptions there, and as we go through the next set of lecture notes, you'll get a feeling for the kind of assumptions we need to make on the parametric model for that kind of statement to be true. So we're going to kind of revisit this issue. Yeah, I don't think I'll say much more about it at this point. So I know this is kind of vague. I put some quotes around it. It's not exactly minimax, but the way to think about it is it then gets large. As the sample size increases, it gets closer and closer to being minimax in some sense. And so it's very, very hard to beat the maximum likelihood estimator. But there are conditions required that will be true, and I'll show you coming up examples where those conditions fail and where the maximum likelihood estimator is actually a poor estimator. Roughly speaking, if the number of parameters is just some fixed number, like in a normal distribution, you would sigma squared, and if the set of distributions varies smoothly with the parameters, when I change the parameters, the density only changes a little bit, then the MLA is going to behave well. You're going to have an optimal estimate. But then I'm going to show you examples where we violate that. So for example, there's some examples where as we get more and more data, we actually add more and more parameters. So if you let the number of parameters increase with the sample size, the MLA will not necessarily behave well anymore. Okay, so we're going to see examples coming up where the MLA sometimes behaves well and sometimes behaves poorly. But for now, think of as a general rule of thumb, a fixed finite dimensional parametric model with some nice smooth solutions. The MLA is essentially minimax. If you want to see, if you're actually curious to see the details, I think probably the best reference, there's a very nice book called Asymptotic Statistics. And this is certainly not required for the course. This is just if you're dying of curiosity. So probably all of you. It's by Vandergaard. And it's a tough book, but it's very nice, and it has all of the very precise statements about what it means to say that the MLA is optimal. That's approximately. So it took a long time for people to sort this out. There was a lot of false claims, and it's non-trivial. Okay, so that's all I'm going to say about that. Section 1.6, I think we'll skip this. It's an interesting example, but it's probably, I realize now, it would have been better to put this example into the next set of notes rather than here. So we might return to this. I know I keep saying this thing with skipping that I might return to, but I'm keeping track of it, don't worry. But I just think this example, called the Hodges example, is a bit out of place here. You feel free to read it if you want, but it's more related to what we're about to do in lecture notes number 9.
So you need a finite sample, like a finite number of parameters, and then the other condition is smoothly what?
We're going to talk actually about these regularity conditions coming up. Yeah. So, all right. So we're finished minimax theory. Hopefully you've got a sense of what it's about. Again, that's sort of just the tip of the iceberg. So now we're going to talk about evaluating estimators and their properties and so on, but taking advantage of the fact that the N is getting large, we're getting more and more data, things simplify quite a bit. We can use all of that convergence theory we talked about to get a clearer picture of what's going on with different estimators. So in lecture notes 9, I start here, by the way, with a bit of notation. So just to remind you, when I write E sub theta, that doesn't mean theta is random. If I take some function, and I write this, what does that mean? It means I'm taking the expected value, and it's just reminding you that the true distribution has a parameter in it, theta. So that's theta. So don't forget that notation. Theta is fixed, it's not random. The other thing is I put a very short review here of all that big O, little o stuff. So in case you've forgotten it, you might want to look over this. I'm just putting that there because I'm going to be using a lot of big O's, little o's. So if you forget, just look here. And there's another piece of reference material here, this thing section 2, it's called distances between probability distributions. I don't want you to memorize this or anything like that, okay? It's just a list of different distances between distributions. And the reason why I'm putting it there is because as we do the theory here, what's going to happen is it's going to turn out that certain distances are going to pop up naturally. And so when I mention a distance, I want you to have a place to look it up. So this is just for your reference. There's the most common distances are, well, we've already talked about this one, right? The pullback ladder distance, remember that guy? The pullback ladder distance between P and Q was defined to be this interval. So we've seen that one before. What else are we going to see? We're probably going to see there's something called the Hellinger distance, which is the square root of P minus the square root of Q squared. That one looks a bit weird, but all of these distances kind of just pop up naturally. It's not like somebody said, I think I'm going to invent a distance distribution. It's because they turned out to kind of pop up sort of naturally in a lot of these calculations. And there's a bunch of other ones here, total variation distance, and so on. Again, you can just look at them as needed. And I even recorded for you some inequalities, like how is one distance is less than the other distance, and so on. This is, again, just reference material. You're not expected to memorize this or anything like that, okay? This is just so you can look things up. And I'll warn you when we're going to use some of these distances. All right. Now, what we want to talk about really here are, when you give me an estimator, let's say data hat n, what can I say about its behavior as I accumulate more and more information? As n increases. What this chapter is about is really just saying two things. We'd like to know when our estimator has two properties. First is consistency. That I'd like theta n to converge in probability to the true value of theta. So that's a consistent estimator. So when is an estimator consistent? And in particular, we really want to focus on maximum likelihood. When is maximum likelihood consistent? And the other type of result we're going to consider is a lot of estimators turn out to satisfy a central limit theorem. That under some conditions, our estimator, especially the maximum likelihood estimator, but not necessarily just the maximum likelihood estimator, that if I take the MLE or some other estimator minus the truth times root n, we're going to see this convergence in distribution to some normal distribution with mean 0 and some variance. Let's call it tau squared. So these are the two properties that are going to prove to be very useful going forward. That sometimes an estimator is consistent. We hope it's consistent. If it isn't, there's a problem with the estimator. And it's even nicer if it's asymptotically normal, because then we can use it to do more things later on, like construct confidence intervals and things like that. So let's think about how are we going to take an arbitrary estimator and prove that it does or does not have these properties. So let's start with consistency. Consistency is convergence in probability. So typically, the way you show that an estimator is consistent, I would say there's two different ways. One is directly, which means just go back to the definition of convergence in probability. If you can actually just show directly that theta hat minus theta, the probability that that's bigger than epsilon goes to 0, then goes to infinity. And that's for any epsilon. Then that's the definition, remember, of convergence in probability. So sometimes it's easy to show things directly. Just compute this probability. But the second way is, do you remember we talked about convergence in quadratic mean? And I said we're going to use that for something else. The reason why we're interested in that is convergence in quadratic mean implied convergence in probability. And convergence in quadratic mean, it suffices to show, now we know the language actually, it's the mean squared error. bias squared plus the variance. What is that? This really is. Remember when we talked about convergence of quadratic mean, we were talking about a quantity like this going to 0. That's how we define convergence of quadratic mean, this. But now, we see this is nothing other than the mean squared error of the estimator. So convergence of quadratic mean, now in the language of estimators, is just saying that the mean squared error goes to 0. And for that, it suffices to have, if I can show the bias goes to 0 and the variance goes to 0, that means the mean squared error is going to 0. That says it's converging quadratic mean to 0. And since quadratic mean convergence implies convergence probability, that implies it's consistent. So to summarize that, if you can show that the bias goes to 0, and then goes to infinity, and the variance goes to 0, that's another way to show that it's consistent. Now, which of these two methods for proving consistency is easiest depends on the problem. Because just whichever one seems easiest is the one that we should use. All right, let me show you a couple of. I'll show you a couple of. I'm going to show you a couple of estimators, a couple of examples where we can show the estimator is consistent, and then I'm going to show you one where it's inconsistent. And then we want to talk about the MLE specifically, but right now I just want to think about general estimators. Any questions about the definition? So let's start off really simple. We'll take the Bernoulli example. And, well, what's the MLE? The MLE is this. So this is a really easy one. We can do this a number of ways, but the easiest way is to say, well, the bias is 0. The variance is P minus 4n, which is going to 0. Therefore, the mean squared error goes to 0. Therefore, it converges the quadratic mean to 0. Therefore, it converges the probability. I mean, we could have done this one directly too, but we now know that in this case, this estimator is consistent. So this is consistent. So that's a pretty easy one. But now, remember we talked about estimating functions as a parameter. Suppose I want to compute this thing which I called before the log odds, which does get used quite a bit. So we know how to compute the MLE of that. We just plug in the MLE into this function. Now, question, is psi hat a consistent estimator of psi? Yes, why? Continuous mapping theorem. This function, log of P1, is a continuous function. Since p hat converges to p probability, any continuous function of it converges to probability. So therefore, psi hat converges to probability to psi. So again, we have a consistent estimate. So there, it was pretty convenient to use continuous mapping theorem. Here's another one. Remember we did this one. X1 to Xn is uniform from 0 to theta. We worked out the MLE. It was the maximum. And you may remember when we first did this, one of the first things we talked about the maximum of everything, was that it converged to theta in probability. How did we prove that? We proved it directly. If you've forgotten that, look back in the notes, where we just said, what's the probability that the maximum minus theta is bigger than epsilon? Here's 0, here's theta, here's the max. So we took an interval size epsilon. We said the probability outside this interval means that all of the observations are less than theta minus epsilon. We computed computed that probability, that goes to 0. So that one we did by direct calculation. We proved, I won't repeat it since we've already done it, but we proved directly that this goes to 0 for any epsilon, and therefore, again, therefore, the MLE in that example is consistent. All right. See, I'm going to jump ahead just a bit and show you an inconsistent. This is actually, I'm jumping ahead to page 5 to show you an inconsistent estimator. Yeah.
To be pedantic for psi and psi hat, don't we have to assume that p is not equal to 0 to apply the continuous mapping theorem?
That's true. If I should be saying here, because we have a problem with that mapping at the boundaries. Yeah. It would actually still be consistent in some weird, degenerate kind of a way, but. Any other questions? So I'm doing example 5 at the top of page 5. Here's what the example is. Suppose I decide I'm going to measure everybody's blood pressure in the class. And suppose I have this device for doing it, which is, let's pretend it doesn't give me your exact blood pressure, it gives me some sort of random variable, which is normal, centered at your blood pressure, with some variance sigma squared. Now everybody will have a different blood pressure, but the sigma squared is from the machine, not from you, so we'll say that's some constant number. And just to be careful, I'm going to take 2 measurements per person. So it looks like this. I go to the first person and I take y11, y12. That'll be now normal, and your blood pressure is mu1, let's say. And variance sigma squared. So I'm allowing everybody to have a different mean here. Then I go to the second person. I take 2 measurements. And that's going to be normal with mu2 with the same sigma squared. And I do this till I have n people, yn1, yn2. Okay. Now, I might be interested in estimating everybody's blood pressure, but I might just be interested in estimating the sigma squared of this blood pressure. What do you call it? I can't remember the name for it. We call it blood pressure meter. Whatever it's really called. So, well, this is all normal stuff, so I can write down the likelihood function. These are all independent. Let's say they're all independent. Keep it simple. Everything's independent. So I'm just going to multiply a bunch of normals together. Now, it so happens that the first 2 have a different mean than the second 2 and so on, but it's just a big product of normal distribution. And yes?
Couldn't we assume a distribution over the use?
That's an interesting thought. That's called a hierarchical model. But so that takes us into interesting territory, but we're not going to go there yet. But that's a good point. We're treating mu just as fixed unknown constants. This point was that in some cases it might make sense that if I'm sampling people from a population and they all have different blood pressures, I can also have another source of randomness. The mu's themselves could be thought as random variables. But we're not dealing with it that way. I'm just going to take the likelihood of this, multiply it. If you maximize it, I don't care about the mu's actually, although you can probably guess what the MLE is for each mu. But the variance estimator just turns out to be I equals 1 to n, j equals 1 to 2. It's basically, it's this minus the mean of these and this minus the mean of these squared, and then sum. That's what it turns out. So let's call that y bar I. Y bar I is just the average of the 2 measurements for each person. So I've left out that calculation. It's quite straightforward. It's also not hard to prove what this converges. This does converge to something. And the way you can show this, for example, is just you can take the expected value of the variance of this thing. And you'll see it converges to its expected value. So this converges in probability, but unfortunately, it converges to sigma squared over 2. So this is not consistent. Now, in this particular example, it's pretty obvious how to fix the estimator, multiply by 2. But usually when we get an inconsistent estimator, it may not be so obvious how to turn it into a consistent estimator. But the point of this example is, why is it that in this example, of computing an MLE, why is it inconsistent? The conditions that you need to have are being violated, and we'll talk more about this in a few minutes. But what's happening here, this is an example, look at the number of parameters. There's n plus 1 parameters. The number of parameters is increasing with sample size. That's always a danger sign for maximum likelihood. Not always, but it's often an example where the maximum likelihood estimator will not be consistent. So we'll come back to that. As I say, I jumped ahead of it there, but I just wanted to show you an example where it wasn't consistent. So what we need, this gets to this basic question then, when is the maximum likelihood estimator consistent? And once again, the complete answer is a little bit complicated, and I would refer again to that book I mentioned before by Vandergaard if you really want to see the gory details, because it is somewhat complicated. I'm going to just try to give you some intuition about when it's consistent and what makes it consistent. So what we do need is some sort of regularity conditions on the model. So remember, our model is still dealing with parametric models. And for now, we need 2 important regularity conditions. So the first one, which this violated, is that the dimension of theta, let's say d, is fixed. So that's violated in the example we just did. Okay, the second condition we need, I'm going to state somewhat vaguely, but basically, this is smooth in theta. So what do I mean by that? Well, think about a normal with mean theta. If I change theta a bit, then this distribution is going to shift just a small amount. You could create weird examples where I change theta a little bit, and for 2 thetas that are right next to each other, they're 2 completely different distributions. You can invent a thing like that by trying to make up something like that. So that's going to be a problem for consistency. All right? So we're going to assume fixed dimension and smoothness. Conditions, if I wrote them down precisely, are actually somewhat complicated. And I opted here to just give you an intuitive description of what the conditions are. And if these conditions are satisfied, then the MLE will be consistent. So proving that, in general, is unfortunately beyond the scope of the class, because it uses tools that we don't have to develop enough probability to do that. But what I will do is show you something very close to a proof. It's kind of almost a proof of this fact. I have 2 of them. I'm going to skip this one. So I have, so you'll see that there's 2 theorems here, theorem 3 and theorem 4. Yeah, should we do that? So theorem 3, I'm going to skip theorem 3. You can mark that as optional. Just put a star next to theorem 3. You don't, if you want, I mean, by all means, look at it. But as I'm looking at it now, I'm thinking, is this really going to give you intuition? Maybe not. I think theorem 4 is going to be better for giving you intuition about why the MLE is consistent. And more importantly, it's also going to show you where this Kullback-Leibniz distance comes from. Maximum likelihood is very naturally related to Kullback-Leibler distance. Okay, let's start this, please. So, actually, to begin with, let's suppose I have, let's just say it's a real value parameter. And what I want to do is just compare the likelihood for now at two arbitrary values, two values. So, well, one of them is the true. Let's call theta 0 as the true value. So we're generating data. We're generating data from this distribution. And intuitively, what I'd like to show is that the likelihood here is high, and that the likelihood everywhere else is small. So let's take another arbitrary value, let's call it theta. And let's start by comparing, how does the likelihood compare to this? Let's look at this ratio. What I'd like to show is that this is much bigger than, in other words, this is much bigger than 1. Well, actually, it's going to be easier to work on the log scale. So if I take the log, what I'd like to know is the log likelihood there, this log likelihood there, is this strictly positive. It's the same as the ratio is bigger than 0. Right? Is everybody with me? So I'm just trying to show that the log likelihood here is much bigger than the log. So let's write out what this is. And in fact, before I do that, saying that this is positive is exactly the same as saying that this is positive, right? If I multiply by 1 over n, it doesn't change anything. The inside is positive if it only has 1 over n to the side. So let's ask the question, is this positive? Well, let's look at what this is. This is 1 over n times the log in that side, 0, minus 1 over n times the log. Let's bring these two together. So this becomes 1 over n times the sum over I of the log. Did I do it in the same order as I did it in the notes? Yes. Now, look what I have. Just think of this here. Let me just call this yi. This is just an average of IID random variables. They're complicated looking random variables, but in the end, this thing only depends on xi. And what do I know about 1 over n sum of yi? What does it converge to in probability? To its mean, right? This converges the probability to its mean. But what's the mean of the random variable? It's the integral of that random variable times the density. So this is converging to the mean of this, which is p of x theta 0 times the function. That's just the definition of expected value. So this is the weak law of large numbers, and this is just the definition of the expected value of this random variable. But I hope you can see what this is. This is the Kullback-Leibler distance between the true density and some other density. And we know Kullback-Leibler distance for two distinct distributions. We proved this when we talked about Jensen's, and we pointed that that's positive. In fact, this is another basic assumption I should have mentioned when we talk about these regularity conditions, which is, I should have put this in here, identifiability. Identifiability. What does that mean? It means that two different values of the parameter better have to be talking about two different distributions. Okay, so if theta 1 is not equal to theta 2, we require these to be different densities. We don't want to have two values of parameter space that are somehow referring to exactly the same density. We just have the same density twice, and have given it two different names. So, that, in other words, that the Kovac-Ladner distance between these should be positive. In other words, two distinct densities. So, assuming identifiability of the model, which is always going to be the model we consider, what we see is that this ratio, or probably this difference, is tending to something, a probability that's strictly positive. So what is that telling us? It's saying that this divided by this is tending to something strictly bigger than 1. So that means that the likelihood of the true value is, as n gets bigger, always larger than the likelihood of some other arbitrary value. That suggests that the maximum should somehow be getting close to theta 0. Now making that leap, making the leap from what we just proved to that it's actually consistent, is where the missing dirty laundry is. Right? This actually takes some complicated stuff to do to show that's true. But I hope this at least gives you the intuition that the likelihood tends to be bigger at the MLE compared to other, at the truth compared to other values. Okay? And that's not quite a full proof of the consistency of the MLE, but it gives you an intuition for the way. All right, how do we do this? So we're over time. So on what day is today? Wednesday. So Friday. Remember, we have a test next week. So on Friday, somebody remind me, because at the beginning of the class, we can decide what's going to be covered on test number 2. There'll probably be all the convergence stuff, you know, convergence of probability, distribution, all that jazz, and then sufficiency, and probably the definition of the, you know, the estimators, remember the moments, maximum likelihood, days, Minimax. I'll probably stop there. Probably this stuff we're talking about now won't be on it, but I'm not sure. Yeah, we'll decide Friday.